Welcome to my next video. So I thought it probably would be a good idea to come back a little bit to things that happened before performing the actual single crystal X-ray diffraction experiment and how to grow crystals. And more importantly, how to grow appropriate crystals. So I had a professor which was very experienced slash quite old, but yeah, he's basically the god of crystallography. So whenever someone asked him, "Oh, how large should be my crystal?" questions like that, he was always answering indirectly. But I think that's the best answer you can actually give to someone. The crystal has to be appropriate. What does it mean? So the crystal size uh, needs to be considered uh, in terms of different factors. So firstly, size doesn't matter as much as the internal order within the crystal. So we want crystals that diffract well. As long as something diffracts well, size doesn't matter. Well, mostly. Okay, so what are the factors that determine whether we need very large crystals or very small crystals? So it depends on the elements that you have. So for example, if you have a lot of transition metal ions in your structure, heavy elements boost the diffraction power of the crystal. So with these, you can go for smaller sizes. Then with structures that are basically carbon, hydrogen, and a bit of oxygen or nitrogen, then you need correspondingly a little bit larger crystals because you don't have these heavily scattering atoms. Another factor to consider is your X-ray source. So if you're working with sealed tube source at in-house laboratory, then you probably need a little bit larger crystals. Let's say, I don't know, 150 micrometers, 200 micrometers. Again, depends on how your crystal diffracts. But if you're going to, let's say, synchrotron source, or you have a rotating anode instruments, which offers much higher photon flux, and also if you have microfocus sources, then you can go for smaller crystal sizes. And in some of the elements, when you work with something super heavy, it's actually not a good idea to have something which is a large crystal, because then you have other problems related to absorption and things like that. So yeah, that's a very good answer. Actually, crystal size has to be appropriate for the conditions and for your material. But okay, so we know that we need an appropriate crystal, whatever that means, in a specific situation, but how to get them? Well, I'm going to briefly discuss some of the methods that I use, and it's worth to add that I'm going to talk about my experience and experience, therefore, of the groups where I worked or work right now. So my experience might not necessarily be your experience. I mostly work with porphyrin derivatives or some nanohoop-like structures, some macrocycles, in many cases consisting of benzene rings connected to each other, forming this kind of nanobelts. So for this type of macrocycles, I just found these methods particularly useful. So let's start with the first one. The first method is actually the easiest one, but usually not really compatible with materials I work with. So just slow evaporation of your solution, and then you get some crystals either on the bottom or on the walls, right? Okay, so first method, slow evaporation. Another method, again, not really suitable for my stuff, is cooling down your solution. You might be lucky. But let's talk a little bit more in detail about other methods. So the first method I'd like to talk about is diffusion, especially in terms of layering one solvent with another. So we take a vial. Let's say our compound is soluble in chloroform. So here we have our compound dissolved in chloroform. Now, a good question, how much material should I use? I mean, if you're working with molecules that are easy to make, you perform reactions on large scale. I mean, some people do crystallizations on 2-gram scale, right? But I cannot do that. Very often I have, let's say, only 5 milligrams of my final product, and I need to do all characterization using these 5 milligrams. So I usually use, and I think that's enough. I use, let's say, 1 milligram of compound, and I dissolve it in, let's say, I don't know, 0.15, 0.2 milliliter of your solvent. Okay, so you put your solution of your material in solvent that dissolves your stuff well, and you layer it with another solvent, let's call it an anti-solvent. In this case, for example, that was chloroform, and that will be methanol. So things start diffusing, and then if you're lucky, you get your crystals somewhere, right? But of course, this method not always works. And you might get some precipitate instead of crystals. And something, a trick, that I really like to do in such cases when you get precipitate, especially if it happens very quickly, let's say overnight, which means that it's just happening too fast. What I really like to do is to take, well, solution of my material, let's say in chloroform, which dissolves my stuff well, and then add essentially drop by drop my anti-solvent and mix it. And I keep adding drop by drop my methanol to my chloroform solution until I see that it gets kind of cloudy or some little bit of precipitates appears, which means that I kind of overcame the solubility barrier. My stuff starts precipitating in the mixture of two solvents, right? And at this point, I don't want it, right? I want to have a clear solution. I add, again, a little bit of my chloroform, just to dissolve all the precipitate that appeared. And in this situation, what I end up with is essentially almost saturated solution in a mixture of two solvents. I take that solution in that vial, close it with a cap, make a small hole in it, and allow it to evaporate. And then usually the solvent, which is the lower boiling one, will evaporate first, and you might get some crystals. So this method works pretty well, especially if direct layering of two solvents produces precipitates, right? Okay. Another method that I honestly think that works best for now for all my stuff, basically for all of my stuff. I don't really use that layering anymore. It's vapor diffusion. So how does that work? I have a larger vial, which is closed with a cap. Inside there is a smaller vial with solution of my compound, and again, I usually use like 0.15, 0.2 milliliter, basically to cover the bottom of the vial, plus give it some few millimeters of space. So I have a few millimeter layer of my solvent, which dissolves my compound well. It's a solution of my compound. But outside, there's solvent, which is bad for my compound. So let's say that was my chloroform. I should have used a different color. So that is my chloroform. And outside, this is, for example, methanol. Okay? And what's going to happen? Vapors of the solvent here will be diffusing inside. The solubility barrier will be reached, and hopefully our crystals will be formed. Now, it really depends on your combination of solvents, because actually, if you use chloroform and methanol, mostly the solvent from the inner vial will be diffusing out. So in such cases, if it's happening, because of that, it will be happening relatively fast, you probably want to increase the amount of solvent to, I don't know, half milliliter or something. So it will be happening in the reverse direction if you used, for example, chloroform methanol or chloroform and hexane. Okay, But in other cases that I'm going to list right now, it will be happening, let's say, properly. So from the outside to the inside. And combination of solvents that I really like for vapor diffusion methods are toluene with methanol, toluene with hexane, and something that I really love, I think is my favorite combination, orthodichlorobenzene with methanol. I love it. Orthodichlorobenzene with hexane. And it's worth to note that it's always good to use basically pure N-hexane. I'm not sure whether pure N-hexane actually exists, but anyway, use something that contains a lot of N-hexane. Don't use things like petroleum ether, because you might end up having in your lattice some weird conformer of some weird aliphatic chain which is not hexane, and it will be difficult to know what is it. So use something that has a large N-hexane content. Another mixture combination would be orthodichlorobenzene and acetonitrile. I really like this. So, if you are working with things such as coordination compounds, some sort of salts, I was working with molecular cages, so some self-assembled cage-like molecules consisting of transition metal ions and ligands that form kind of capsules. What works really well is a combination of acetonitrile and, for example, diethyl ether. The problem with diethyl ether is that it diffuses quite fast, right? It's really low boiling solvent. So usually you should put such mixture to a fridge, or even not fridge, actually freezer, to make the diffusion slower. Otherwise you just within hours get some amorphous or microcrystalline precipitate. In order to slow it down, we put it in a freezer. If you don't want to use the freezer or just use another combination of solvents, what I really like is to replace diethyl ether with diazopropyl ether. And then you can actually do that even at room temperature, because diazopropyl ether has much higher boiling point than, maybe not much, but well enough, high enough, high boiling point than diethyl ether. Another thing why it's not always a great idea to use diethyl ether because of its boiling point is that once you pick crystals, if your crystals contain co-crystallized solvent like diethyl ether, it will be, of course, evaporating as well. So it might be that your solvent loss will be so quick that your crystals will get destroyed, they will lose long-range order, and you will not get any decent diffraction at high angles. Okay, another combination could be DMSO with diethyl ether or with diazopropyl ether. I know that some people also use DMSO as the inner solvent in the small vial and toluene in a outer vial. So I've shown you my solvent systems I have really good experiences with, and I should have probably added some of them here. So really that layering method or this, so slow evaporation in a mixture of kind of saturated mixture of two different solvents, I use it exclusively almost for chloroform hexane, chloroform methanol. Yeah, that's it basically. In my experience, what works. I'm now really going for vapor diffusion. It works well in my hands, especially this and this solvent systems. I just completely love them. So if your stuff is well soluble in orthodichlorobenzene and not that soluble in methanol or acetonitrile, you can try it. If you're doing, for example, co-crystallizations with fullerenes, then fullerene C60 and C70 are much more soluble in orthodichlorobenzene than, for example, toluene. So it's also a good choice because of that. Okay, so I think I told you about all the methods that I use. And I think it would be also a good idea to mention a little bit how to pick crystals, right? So, picking crystals, mounting them on a loop to transfer to the diffractometer. So, In general, I always treat all my samples as solvent loss sensitive. I do everything super quickly. So the way I usually do it, you can do it two ways, at least two ways. I put a spot of oil on my glass slide. The oils that I use are usually quite dense oils. I have very good experience with very dense oils. I use NVH oil. I'm not sure about Europe, but in the UK it can be purchased from. I'm not making advertisement here. I just know that you can buy it there. Jena or Jena Bioscience. Also very good oil is paratone oil or parabar. But the problem is that it's not possible to buy it anymore. I have it from my secret sources, let's say, but you probably cannot buy it anymore. I've also seen it and some synchrotron beamlines that they have a bottle, which will be enough for ages. Definitely there's one at I-19 at Diamond, at P24 at Petra Dry, Petra 3, sorry, at Desi in Germany. Not sure about others, but you cannot probably easily buy that one anymore. But NVHL is perfectly fine. It has very similar properties to Paratone. Another oil that you can use are these perfluorinated, for example, Fomblin YR 1018 you can get from Sigma. But the problem with perfluorinated oils is that firstly they are a bit more liquidish. So sometimes, especially if you go for maybe not that low temperatures during measurement. If you want to do some, well, relatively high temperature experiments, I don't know, 10 degrees or room temperature even, it's always better to use more dense oil. But in general, that oil is fine as well. But remember that this perfluorinated oil really don't like to cooperate with things that have these fluorinated ligands or counter ions. There's this barf, and it's got four groups like that. Barf and ion, they really don't like perfluorinated oils. They tend to dissolve in them very quickly. So you have your nice crystals, put them in perfluorinated oil, and it's dead. It's gone. Because it dissolves in the oil, they just form some weird hydrogen type bonding or something. So always be careful when you have a lot of perfluorinated compounds. They are not very compatible with perfluorinated oils. So I really recommend NVH or Paratone. So anyway, what do? I put my spots with oil on the glass slide, and then let's say I have my vial with mother liquor, and there are some crystals, right? So usually to pick crystals and transfer to glass slide, I use, well, normal long needle. I cut the end of the needle a little bit to make it a little bit more blunt, not that sharp. And then I put the end of the needle in oil in a way that you have a nice big fat drop of oil. I put it inside my vial with mother liquor, and very quickly I kind of stir it a little bit next to the crystals to kind of catch them in the oil to make them adhere to the oil, and then I transfer it very quickly on the slide, and then I pick it, right? Another method is you basically take your glass slide, and in this case I would probably go for rather large oil kind of drop. You can also smear it in a way that it's got large surface. And then you can take a pipette and suck some suspension of your crystals in a pipette. My drawing, my drawings sound not great. So you basically transfer a suspension of your crystals in a pipette to your oil in a way that, crystals will fall down and they will be protected by oil. This method is not recommended if you're working, under microscope. There's no good ventilation, and you're using solvents that are very toxic, like orthodichlorobenzene or benzene, or I don't know, carbon disulfide, because you really don't want to breathe in these vapors that are now on the slide and evaporating, and you catch them straight to your lungs. So, in general, recently I find this method with picking crystals directly from the mother liquor with needle with a bit of oil much better. The only problem is that then you contaminate your mother liquor, right? So if yeah, if someone wants to reuse it, reuse the crystals to redissolve them again and try another crystallization, I would recommend to wash your material with hexane or something like that to wash off that oil that you've put on the needle. If your compound is not soluble in hexane, then it's nice because you will get rid of the oil and not of your compound. You can nicely wash the oil off. Okay. And another thing last thing I wanted to cover was, what if I have air sensitive samples? So firstly, you need to grow them in inert conditions. You can either do it in a glove box or you can use, I can put a link to my paper where we show an image. It's kind of apparatus which enables us to set up crystallization by layering method and flame seal an ampule. So we have a nice flame sealed ampule. There will be no oxygen going inside. We can leave it for years and it will be stable. So glove box or flame sealed ampules, right? So let's say you have your sample in a glove box. What happens then? How do you transfer it to the diffractometer to not allow it to die immediately? That works pretty well for like carbon ions or in general very unstable organometallic compounds that are very air water sensitive. So what I usually do, I put that material, again, a bit of oil in a glove box. Before putting your oil in a glove box, you want to dry it. So I take not too much oil, let's say half milliliter of oil in a vial, usually the very dense oil, and I leave it under Schlenkline under very good vacuum overnight to remove any traces and, well, most of water or oxygen. Then I put it in a glove box for some cycles before putting in a glove box, and then I store it in glove box in a closed vial. So I put a bit of oil on my glass slide, and then you pick crystals as usual. Just take a little bit from your mother liquor or evaporated material that looks crystalline, whatever. What happens next? Well, you need to put it under diffractometer, right? So how to safely do that? I usually take like a jar, like a glass jar with a nice cap on it. So now everything is under argon. I close the jar in a glove box, and then I literally remove it from a glove box and literally run to the microscope, pick the crystals super quickly, and mount on a diffractometer. If you cannot run directly to microscope and to diffractometer because you're, I don't know, giving your sample to someone from different university with better source or detector, or you have beam time at synchrotron. What I found very useful is either, if you can and you think you're brave enough, you can flame seal suspension of your crystals in oil in a glass ampule, or maybe Beamline has a glove box where you can do the same thing there. Or something I really like is to use these J-Young NMR tubes, or in general J-Young tubes. So I basically put a little bit of oil on the walls, then put a little bit of my crystals immersed in oil, put them in, I close it with that J-Young cap, and it will stay for days, if not probably weeks. And I can just transfer that J-Young tube with a bit of my crystal suspended in oil to the beamline, for example, or to give it to some crystallographer from other university who has better diffractometer, and they can then take a needle and again transfer these crystals very, very quickly to a glass slide under microscope, mount, bang, and we got a structure. So anyway, I hope what I've told you was useful. I know that if you're a protein crystallographer, these methods of crystallization probably are not going to work for you because you have these fancy buffers and yeah, hanging drop methods, things like that. But if you're working with, coordination compounds, some macrocycles, porphyrins, I really recommend these methods, especially the vapor diffusion with my lovely orthodichlorobenzene and methanol solvent combination. So thank you very much. I hope you learned something, and please share it with your colleagues, with your department, with your crystallographer, whatever. And if you know some other fancy methods for crystallization, let me know in the comment. Thank you.